So in this video, we're going to talk about one further application of Cauchy's integral formula. I'm going to define a function f of z to be 1 over 2 pi I times the integral of f of zeta over zeta minus z d zeta. And what we're going to do is we're going to differentiate this function. We're integrating over some nice curve, some nice path gamma, and we're going to integrate. It's a closed path. So closed, when I say nice, what I mean is closed, piecewise smooth, simple, positively oriented. And what we're going to do is we're going to differentiate f. And what we're going to do is we're going to make a big assumption here, and we're going to assume that we can differentiate under the integral sign. In general, that's not obvious at all, and in many places, it's not a valid thing to do. In this case, it turns out to be valid, but I'm not going to prove that it's valid. You're just going to have to either trust me, or we're actually going to come back and we'll revisit this later in chapter 8. So for now, I just want to show you kind of where the formula comes from, or one way to think about the formula, or one way to remember it. So what I'm going to do is I'm going to differentiate f with respect to z, and we're going to assume that we can differentiate under the integral sign, meaning that we can take the derivative and push it inside the integral sign. Now, remember that the derivative is a limit, the integral is a limit, and interchanging limits is a non-trivial operation. That's the thing that in many cases will fail. In this case, it turns out to be fine. So what we're going to do is we're going to differentiate the integrand, f of zeta over zeta minus z. We're going to integrate that with respect to z. And of course, f of zeta is going to be a constant. It's independent of z. So we can bring that out. And that's fine. And then the integral of 1 over zeta minus z is going to be, let's see, zeta minus z squared. So we're going to get zeta minus z to the negative 2. So that would be times negative 1, but then also times the negative 1 from the inside. So I'm thinking of this as if we have zeta minus z, that's a terrible zeta, but if we have zeta minus z to the negative 1, then the derivative would be negative zeta minus z to the negative 2 times the derivative of the inside makes that a plus. So you end up with the same quantity, but with one larger power there. And that turns out to be f prime. And then let's do this just one or two more times to look at the pattern. So f double prime of z, we're going to do this again. We're going to push the derivative inside. We're going to differentiate this quantity now. So we got 1 over 2 pi I integral over gamma, f of zeta, all over, and then we're going to do this same differentiation again. And we're going to end up with negative 2 times z minus zeta minus z to the negative 3 times negative 1. So altogether, that's going to end up being 2 times f of zeta over zeta minus z cubed. And then one more time, the third derivative is going to be, let's see, 1 over 2 pi I. Actually, we have a 2 over 2 pi I because we're integrating from before. Integral, we're going to have f of zeta over, it turns out to be zeta minus z to the 4th times 3. So this is going to be a 6 over 2 pi I. And then the next time we would do this, just notice what's happening here. The next time that we do this, we keep multiplying by this power up top. So the next time we will get this thing times 4 all over this to the power 5. Okay, so that would be the fourth derivative and so on. And so this tells us actually a few things. So first of all, in general, we know that the kth derivative is going to be k factorial over 2 pi I times the integral over gamma of f of zeta over zeta minus z to the k plus 1 d zeta. Okay, so it turns out that that's the kth derivative of this function, and that's a very useful quantity for us. Okay, so in general, the kth derivative is going to have that formula. Now, this tells us something right away, and maybe this is obvious. I don't think it is, but if you can come up with a formula for any derivative of f, this tells you f is infinitely differentiable. So f is infinitely differentiable. Okay, and that's a big deal. What this says, and this is in stark contrast to the way that functions of real variables work. If you have a function of a real variable and it's differentiable, it can be differentiable once, it can be differentiable 3 times, so and maybe at a certain point it stops being differentiable. In the complex case, that doesn't happen. If you start with a holomorphic function, it turns out that that function is infinitely differentiable. You can differentiate it as much as you want. Okay, so that's a big deal. We're going to use that over and over. So in short, if f is holomorphic on G, so we'll call this a theorem. Okay, so if f is holomorphic on G, on a region G, then f is infinitely differentiable on G. You can take as many derivatives as you want. Okay, and there's some good examples of functions that are differentiable only once or twice over the reals. But it turns out that that behavior just doesn't happen if you start with a holomorphic function in the complex plane. Okay, so we've established 2 things in this video, which I think are very important. We have a formula for the kth derivative that's kind of a generalization of the Cauchy integral formula. So if you think about the original function f of z as being the 0th derivative, then everything works out. Okay, so everything kind of just falls into place. And the second thing that we learned is that every holomorphic function on a region is infinitely differentiable in that same region. Okay, so that's a big deal. We're going to use those facts over and over.